So, today we complete this topic systolic implementation. Actually, there is nothing much, it is more of hardware now. What we are doing that time is just quickly Qn this one we are minimizing, and we said that Qn should be such that this matrix is triangularized. Okay. And you find out the solution for the upper triangular part, those will give the optimal filter coefficients, that is standard. So, actually we had this matrix Qn was, what was our Qn? Qn was sequence of rotations Gmn dot 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 G1n followed by this matrix Qn minus 1 0 transpose 0 1, which I called Q bar n minus 1, right. This is Qn, this will work on this works on this part, will give you square root lambda times Rn and then a chunk of zeros, okay, and followed by, and last row will consist of the new entries. This matrix working on this data matrix, this lambda n to the power half x n, we have seen yesterday also, happened many times, will give us to what? One upper triangular component multiplied by lambda to the power half. That upper triangular component will be R n minus 1, then followed by a chunk of zeros, and last row will consist of the new data x1n, x2n dot 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 x m n. Okay. And on that this will work on rotations, this will so that the last row will be finally annihilated and new R n will be formed. Okay, that was the thing. In practice, you do not have to compute this Q at all, you just have to carry out these rotations. Okay, m rotations you have to apply, and as you go on doing these rotations, and this part I call Tn, you have to apply this thing here also. Here it means here also the same Qn. So, Gmn dot 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 G1n into your this Q bar n minus 1, this will work for this. This will work on this, okay, this will work on this vector, and out of which Q bar n minus 1 while working on this will give rise to what? Two components, I mean it will give rise to this thing, this part, this working on this will give rise to Gmn dot 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 G1n into square root lambda upper part, square root lambda lower part, and that last component, right. Q is not required. I know the upper and lower part for the previous index, just multiply by square root lambda, put the new L guys, apply the same sequence of rotations. Okay. So, first I have to carry out this, then from the upper the first m components, that is m into one part, I will take that out separately. Once I do this matrix, the upper m plus 1 component will be the new un, that will be taken out separately, and here the triangular matrix. I have to solve that and get the optimum filter coefficients. That is the business. Now, to do that, I take an example. Yesterday I was doing the systolic implementation, but I was halfway. You know, there are some issues involved there. So, just to do that, let us take the case of m equal to 4. I took m equal to 3 yesterday. I thought m equal to 3 is too less. M equal to 4. Okay. And we are at index n. M equal to 4. We are at index n. And also, we will have operations like this. You know, we will have some processors like this. First, this processor supposed to store some data x and a fellow comes u, then it will generate two components C and S. How? Yesterday I told you that there are 4 possibilities. One is that it is here both x and u are positive, we rotate this way. In that case C will be positive, cos theta cos minus theta same, but S will be in this direction. If you do, then in that matrix, rotation matrix, S will come out to be positive. Actually C minus S, but since S in this direction, C S, that is our convention. On the other hand, if it is here, again theta will be in this direction, C will still be positive as equal, but S will be negative. Okay. Again here if it is, you rotate only up to this, C will be positive, in positive sense positive, S will be, because you are going in this direction, S will be negative. And if you are here, you are going in this direction, C will be positive as it is, but S will be positive. So, you see C is always positive, and how much is the C value? You take this, give in x, take the mod, find out this length, take the mod, take the ratio. That is the value, and give a sign to that equal to the sign of the x. So, yesterday you wrote those mod x by, those things are not required in hardware, they are more complicated. The sign of a number is very easily found out in hardware. You have to take the sign bit only. So, it's better this book is old style, it's better not to use those kind of things. So, what it will do, and the special case when this u is 0, that time even no computation is required, so that case we take out separately, otherwise the remaining part also takes care of that. But why do the computation when this is trivially operates? That is why I said for u equal to 0, C is obviously 1, S is 0, and this x will be replaced by x itself. Okay, no need to do any rotation and all that. So, x goes to x. Okay, else what happens? You find out x prime. X prime is, you have to bring in, this is that triangular part, that element, na? It's like you understand where from this element comes. There is an upper triangular part, say consider the first entry, that and u the last row. So, naturally when I do the rotation first, square root lambda comes here, square root lambda term is this x and then 0 0 0 and then u. So, when you rotate, you find out this new length lambda okay. Then your C is, so whether you are x and u here or x and u here or x and u here, you get a net value. This is a positive sign. Then C is sine of x times x prime. I am already taking the plus value. It's fine. And S will be, S magnitude of S is always u by this length. So, that part I first write, magnitude u by your into, when you see, if you just count those cases, you see when both this and this are positive or this and this both are negative, then only S is positive, otherwise negative. So, it is the AND function actually. So, this is sine of, if you take the product x times u, when both are positive or both are negative, either case sign will give you plus. Do not think in hardware you really have to multiply the two and take the sign. Sign of AB is sign of A into sign of B, which is actually a logical AND operation. Okay, I am not writing all that. This you know, this is elementary hardware. This is S, and then x will be replaced by x prime. This is one processor and there is another processor. This kind of processor. Here if it is take CS, they will propagate through it, same CS will come out. So, along this line no processing. If a U comes and if it stores a value x, U prime will come out and x will be replaced by x prime. What are those things? What does it do? What is U prime in terms of all this? U prime will be, U was that last row entry, you are rotating, you have found out CS parameter, using that you have taken any other column on that Rn that matrix. You understand? So, first column you annihilated the last row, last element, that becomes 0. You got a C and S parameter. So, you have to apply the same rotation on the other columns also. So, those elements in those columns, last row is this U and top row element, first row element is here. Okay, that has to be rotated. So, output will be, this will be multiplied by square root lambda. So, output will be C square root lambda x, sorry, not C, this is x prime first, x prime, sorry, x prime will be C square root lambda x plus S U, okay, and U prime will be that cos and sine and minus sign minus S and x prime goes to x, okay. With these descriptions, now suppose I am dealing with the case with m equal to 4. As an example, capital M equal to 4. With these descriptions, I do like this. I will be writing within bracket 1 comma 1. Our starting index is n equal to 1, not 0, n equal to 1, dot 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 current index un, sorry, it is I am still not doing the filtering case, it is more general case where m defined signals are there, x1, x2 up to xm. Okay. In the filtering case, other things are just delayed versions of this line. I can afford to be general here, even here. What are these things, you know? At the n minus, at the nth index, what you have? You have one upper triangular matrix, that is square root lambda times r n minus 1 followed by zeros and then last row, isn't it? So, you have this thing, square root lambda times, say, I am not writing this element, these will be stored here. Upper triangular. Then dot 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 zeros, and then last is x 1 n, x 2 n, okay. What I mean, this guy, see, look at this matrix, 1 comma 1th element, this is stored here, 1 comma 2th element, this guy will store, and it will after rotation update these values also. Currently at nth index, those values, this value is stored here, 1 3, 1 4 stored here. And similarly, there is a d. What is there in the d? Square root what is d after all? The square root lambda, I using those notations only, I rewrite what I wrote earlier. On this I have to do the rotation, like here also on this I have to do rotation, here also on this I have to do the same rotations. Rotation will be derived from this matrix and applied, also applied on this. Okay. So, when I say 1, basically the top entry is stored, top entry of this vector. I am not bothered about this, do not need to store this. Why? Because I am always bothered about the first m cross 1, that is 4 cross 1 component, because only that will be used in the solution for finding out the filter coefficients. Here I am not bothered. Here I have got 4 entries, so there will also be 4 places to store. There is a top guy, then there will be other fellows also. Okay. So, what this guy does, at this moment no pipelining, nothing, everything is done all together in one cycle, everything done, and then again new data wave, data front, I mean data vector moves in, that way you see. So, what this guy does, obviously it computes the CS parameters, you all know, and I have given the algorithm. So, it will give the CS parameters here, and that will propagate, because that is how these processors are, whatever comes through they propagate like this. Here they propagate, but no use of this. What does this guy do? He applies the same CS on what? This fellow, that is this, and the new guy that is entering. Okay. Rotates them so that what comes out? You are applying the rotation on this fellow and this fellow now. Rotation of as of C and S derived from these two, applied on these two, out of which this will get updated to some value, that will come back here. Please note this, that will come back here, and this will get updated to some value, that will come out. Why I want to store this? This is this and this, after that C times this and S times this, and it gets changed to some value. Why I am also bothered about storing that here? It is because next time at n plus 1th index, when a new row comes, x 2 n plus 1 will come, again new C and new S will be applied on them. So, this rotated value has to be stored. Okay. This value has to be annihilated, but this value, modified value, has to be stored for use at the n plus 1th index. Okay. So, that is getting stored, and this new guy is coming out. That new guy and this fellow, I have to do the rotation so that is annihilated. So, this will then go to another fellow. This will be storing which element? 2, 2, diagonal elements are stored. This element is stored here in this processor. With that element or the new value of this, it will compute new CS parameters. This rotation was applied on this. When you take this column, even in this column, this value and this value are altered. This new value is stored here for future use at n plus 1 at the index, but this altered value comes out here. That needs to be rotated by the new CS that comes out of these two guys. That will be applied on this, S applied on this, C on this, S on this, say, for one rotation, one of the two. C on this, S on this, and minus S on this and C on this. Okay. That is what is done here. So, this guy stores this element 2, 3. And why only 2, 3? You are applying the rotation on these two, you have to do on these two also, out of which this, after the first rotation came out of this value got modified and got stored here. What came out on that, the new rotation coming from these two will be applied, on this and this. So, this is stored here. Same CS will come. Here 1, 3, 2, 3, that is this was rotated, then these two were rotated, then this fellow, this and this needs to be annihilated. So, this comes out, this value is stored here, out of those two new 2 C and S comes out. So, this is annihilated, that will work only on these two, isn't it? Only these two. So, this value will be modified, stored here. This is 3, 4. 3, 4, third row, fourth element, and this value will come out, that and this will be rotated, so that this is annihilated. Okay. Now, comes to this D. First set of rotation, one CES parameter work on the last guy and first guy. First guy stored here, last guy enters, rotate. This is simple hardware. So, first guy modified value comes here, last guy moves here. Then first but one, but second guy, and again this new last guy. Second guy was stored here. Second guy and the new last guy. On them this rotation. Modified second guy stored here, a new last guy comes, that and the third guy on these rotations. Modified third guy gets stored, new last guy comes out, on that the last rotation. So, understand all these values that are stored down, they are important, but because these values will give rise to that upper triangular matrix. After the Rn will be content now. After this entire operation, all the operations done, this part will consist of Rn, isn't it? This appearing to be lower triangular because of my drawing, but you can easily identify the elements Rn, and this will give rise to that upper part which needs to be solved. Solution is done separately by back, because it is a upper triangular solution, and that is done again by an array, linear array, that I will come to. But this is now those who have done this is just for triangularization of the matrix and corresponding rotation of the upper part of this vector. Now, here as such, this computation you have to do, followed by this, followed by this, followed by this, followed by this, these two. You see, if I have to do the entire computation, so much of time will be taken. Before I allow the n plus 1th data vector to move in, I have to complete this, that result will be here to complete this, both this, which then this, you can find out the total time required. That will be quite huge. But those who have done my VLSI for telecom course, or those who know pipelining, all that, at least in principle, I can bring down the complexity very, very much here. Do you have an idea about pipelining? So, pipelining is like, suppose there is a pipe, I am throwing stones, this is how I taught them. So, I am throwing stones through the pipe. Each stone takes some time, say tau, to come out of the pipe. Once it comes out of the pipe, if I send the next stone, then I am throwing stone only at a rate of tau. Okay. But suppose I say that, okay, I won't wait for the stone to come out of the pipe, let it go little bit and then I throw another, then little bit another. So, my rate of transmission will be higher. So, instead of pipe, it is a total process, and instead of stone, it is data. Instead of waiting for the data to be completely processed and then coming out and then sending in new data, let me send one data and let it be processed partially and then passed on to the next stage of processing, and then I will give in another data. So, that means I divide the entire process into small processors. For synchronization, I keep latches, so that one cycle, okay, each of them takes time less than my clock cycle, otherwise there will be conflict, but I give one cycle to it, or less than one cycle, it does the job, only after the cycle is over, passes on to the next guy, so on and so forth. So, that means I have to break that job into small sectors and introduce latches, pipeline latches. Here I do not have to even break, these are already broken. So, suppose here I put a D for flip flop, one D. Those who have done my course, they know I will apply card set here. Pradeep Choudhury knows more than me here. Okay. D. Again here D. Again here say D. I am going horizontally, not vertically, I am going horizontally. That means in one clock cycle, these operations will be done. This followed by this, followed by this, followed by this, followed by this. Once that is done, then you pass on the stuff in the next, and once it processes this result, you can accept the new data x1 n plus 1, x2 n plus 1, like that. Okay? You do not have to wait for the entire thing. So, it comes down. I can go vertically also with the same logic. Then you take it as a home task to see the sequencing of data, how the data moves through the array. Here, when it was only horizontal, one cycle, all the processing, then next cycle, that output moves here, and x1 n plus 1, x2 n plus 1, they come together, they move here. But here it will be little, it's delayed in both ways. No? So, that sequencing, the data movement, you just have to work out which data going where and all. Okay, but D. Correctness will not be affected. You can verify that. So, that means my clock will be governed by what? Whichever of this processor takes maximum time, because all processors are pipelined. These latches are there between every two processors, whether of this kind or between them. So, apparently this processor takes more time because of the square root computation, multiplication, all that. So, if it takes tau second or tau millisecond or microsecond or whatever, that will be the determining factor in my clock. My clock period just has to be tau at the minimum or it can be greater than tau, that is all. Those who know my course, they know I am applying Cartset here and then applying Cartset. That is very obvious. Those who have done the course earlier, VLSI or Telecom, for them I am saying. This is what the forward path, I am applying Cartsets. Okay. That is one thing. Back substitution, is just written in an algorithmic manner, but I will explain. I will just mention from the book. What is back substitution? That is, you have got a triangular section. Say A, B, C, D, E, F, G, H, I, J, and then zeros, and say W1, W2, W3, W4. Zeros I do not care, this part is this part equal to say your upper matrix U1, U2, U3, U4. What I do, first find out W4 by solving the last equation, then propagate back, use the same W4. So, that from the second row I into W4 known, find out H, and then W3, W4 known. So, propagate back F into W3, G into W4, find out, subtract, find out W2, and so and so. So, it is a back substitution. Okay. Again, this can be done by an array, and it is a linear array. Instead of instead of working out, because time is less, I will just write it down from the book and explain to you. That suppose I have indices like this. For I first write down, we will go down m to 1, m minus 1, m minus 2, like that. This is given starting value 0. You will see just writing in an algorithmic manner, we will have it verified. Instead of developing the algorithm, I am just writing and explaining, because time is short, I want to wind up today. Okay. This is 0. Then for k equal to m to I plus 1. So, that means when I equal to m, you do not execute the loop, because m plus 1, sorry, just a minute. Yeah, okay. Let me write down first, then that statement will be. This U is for that upper UN, ln, that upper part of the matrix. You remember UN vector and ln vector, I am bothered only about the UN, and UN the components will be U1n to UMN. This is how I will write the components. So, UIN J di I whereby RII. Let us see what it means. Suppose m equal to 1, I equal to m, so Z m m is 0, and here k equal to m plus 1. Let me see whether I am writing things correctly. I am come to this later. WIN, WM, last component. I am coming to this later. WMN, you see, it is like last component here, minus ZMM, that is 0, divided by simply RMM. That is the last equation. RMM here and here, by RMM, WM. Okay. That time this loop should not be executed. I do not know whether I am.
We are actually going step -1. So it is m to 1 means we are going in a negative direction.
Yeah.
So
this won't be executed. Yes. Yeah, good. We are going in the negative direction. Our bottom what? K and I both are going from m to 1. So next time I equal to m minus 1. This time I have no I equal to m minus 1. I am here. This is not 0. Only when I equal to m, this is 0. Okay. your consider the k, k means what? M to m, so only one loop, and that times z m minus 1, z m minus 1, what is k? M, that is 0, and this is that m minus 1 m n into the new value, this guy, m minus 1th row, mth column, that guy into this, and this is 0. This part I am giving a name, z m minus 1, m minus 1. Both have to be same, then only I will bring back here, na? And that comes u m minus 1 n, that is last guy, minus that part, divided by this component r m minus 1 m minus 1, that will give you this. Then you go for I equal to m minus 2, I equal to m minus 2 means k equal to m, then m to m minus 1, k equal to m case, then k equal to m minus 1, isn't it? So, twice k equal to m means, after that it will be clear, k equal to m means this is 0, whenever k equal to m, this top value is 0, because to the right of this there is nothing, 0, na? That is why this is 0. The starting is m here, m means this corresponds to the column, last column, m minus 2th row, last column, that entry times first guy, that weight, mth weight. Okay, that will be given a name here. What name? M minus 2 and m minus 1. Then that will be brought back here, because k is now first m, then m minus 1, that will be brought back here. And this is one column to the left now, that was mth column, now m minus 1th column, one column to the left, that times m minus 1th weight, that with this, then it becomes z m minus 1 m minus 1. Then you bring back here u m minus 1 minus this by, okay, this is how it is. Actually, this is like writing the algorithm, you know. Physically, we know how to solve it, it is just algorithm form. And this is done through a linear array. I will just again, you know, I mean, do like this. Schematically, actually, what is done is, here it is, you know, the backward forward movement. I mean, in the triangular section, everything was forward direction, no feedback, but here is a feedback kind of thing. Feedback because of the back substitution. That is the feedback thing. Okay, that is why it is back substitution. Weights will move in this direction. What this guy does, it will generate weights. This weight, I will not, I am just drawing the schematic. Okay, this will do, this operation will be done here, and this operation will be done here, using exact variable names and all that you do, but these operations will be done here, these operations will be done here. In the very starting index, you know, when I equal to m, this is 0, you are finding out, and these r values are stored, they are all available, r values are stored, r m m is stored here. Using r m m and u m n, this guy first find out w 1 m. Then w 1 m, and from here that time 0 comes, w 1 m, and this guy has stored or m minus 1 m, okay, that into this. Do I have to do this sequence, or you can do it yourself? Because, you know, I mean, I have to complete that part, that other part, that linear dependence independence thing, that for n less than m, when I got all 0 columns coming, you remember that part also has to be completed. Can you quickly see this? Here the weights will move, and here j's will move. New z from old z will be computed here. When this z's computed, when it becomes z I comma I, then only it reaches here. That minus the stored value, when subtracted from the stored value, divided by the stored value, that will generate new weight. I suggest you work it out. Because for another 5 minutes I do not take a class, then that class, remaining 45-50 minutes will be vacant. So, that is not something good. So, I have to wind up here only. If time permits, I will come back to this. Come to that issue where I had got n less than m. That time I said that all 0 columns will come up, and therefore, QR that way is not possible, because my first assumption on QR factorization was that the columns are linearly independent, and therefore, you do Gram-Schmidt orthogonalization, you get mutually orthonormal vectors, and then go outside the space and take few more orthogonal components, you get a full unitary matrix UN, a Qn. Okay, that is what I said. But if the columns are linearly independent, not linearly independent, you don't get that. Okay, so what to do there? Remember, all throughout the derivation, I have not changed the order. I have not changed the order. Order was fixed. We moved from nth index to m plus 1 index, where m was m. M was never changed to m plus 1 or m minus 1. But here, what I will do, at n equal to 1, see my matrix, I will write like this: 0, my data starts at 1, this is n equal to 1, and you now consider, yes, now consider, I will be considering this particular case, linear dependence independence, for the filtering case. Filtering case means filtering with pre-windowed. Pre-windowed means whatever will be the first column, Z inverse of that will be second, Z inverse 2 of that will be third, and like that. I mean, likewise, as we did in the recursive least square lattice. And 1 is my starting index, so 0 will be there on top always. Unlike there, here my starting index is n equal to 1. Like that. One, two, three. Say m equal to 3 we have m equal to 3 case. What I will do, at n equal to 1, I will not consider these 2 rows, columns. My purpose is to find out at n equal to 3, I should be able to get that Rn matrix. At n equal to 3, because my final m is 3. At n equal to 3, that is realized, and after that n moves, but m does not change, I will not have that problem. Okay. So, n equal to 1, I consider only this part, as though this matrix is given to me. This I will view as square root lambda R0, no problem. R0 is my 0. This and this, I do rotation. If I rotate, this will move up, 0 will come down. Okay. So, then what I get, at n equal to 1, I only rotate these 2. Okay. That means your this square root lambda 0, u1 moves here, 0 comes here. At n equal to 2, then what is the situation? At n equal to 2, I will take one more column. Remember, always number of row is greater than number of column, and I am not having all 0 column coming and all that. Here it was this much, here it is this much. So, that the dependence problem which was coming because number of row was less than number of column and all 0 column was coming, that is not. All 0 column in the case of filtering, otherwise number of row less than number of column, and therefore dependence coming, that is not present here, isn't it? Especially with this kind of setup. These two are linearly independent, E1 is non-zero, I am assuming, E1 is non-zero. So, this cannot be written as a multiple of this. So, this I knew, that is why I am worrying, okay. Obviously. So, first I take this part, one component, no problem. Then I take this much, 2 components, but clearly they are not dependent. This cannot be multiple of this. This is non-zero, E1 is non-zero, assume. So, this time what is the structure? I have got one data here, one data 0 here, 0 0. These 2 0 put together and data here, that will be like 1 R, and that I will view to be square root lambda R1. That is, I am taking this much now. So, that will be what? N equal to 2. I have got square root lambda R1, that is Rn minus 1, followed by these 2. U2, U1. How many columns? 2 columns only. 2 columns only. Okay. This upper part 0 0 here, U1 moved here. That part I am calling square root lambda R1 and U2 U1. This I can annihilate. Dependence does not come. Just 2 rotations will be required now. Here 1 rotation is required, 2 rotations will be required. So again zeros will form and one this thing will come up, upper triangular matrix. Okay, I have to multiply that, like here I multiplied by square root lambda, that time I will have to multiply R2 by square root lambda, and I will take this much at n equal to 3. So, till that n equal to m situation arises, there is an order updating, order wise movement. Okay. Do not take all the orders at the very starting index, that is the key. So, that dependency is avoided. At n equal to 3, I take all the 3. What I already have up is these 3 zeros, one upper triangular fellow, these 3 zeros, and this part. Okay. Multiply the upper triangular part by square root lambda R2 followed by U3, U2, U1. Now 3. Again 4 rows, 3 columns, and obviously this linear dependence is not there. This is not a linear combination of these two. I mean, you multiply the 3 by C1, C2, C3, add, they cannot be 0 altogether. So, this you have seen in that RLS lattice case also. So, obviously again I can rotate it, I can triangularize it, this can be annihilated and I get R3, this gives rise to R3 zeros. From now onwards there is no problem, because I have reached a situation where n equal to m. M will, I mean, after that on a new and new rows will come up and therefore dependence will go, possibility of dependence. Okay. That is all for this course. I will take 2 more lectures, but that will be not for you, because it is 38, 2 more lectures, appendix 1, appendix 2, that will be on elements of estimation theory. So, those were the PhD students and want to know little bit of estimation and other things, I can tell you sometime maybe during this end sem or afterwards. I will take 2 classes, special classes, not for this course, I mean not towards credit purpose, but for this video recording thing. Okay, that will be on something on estimation theory, 3 basic kind of estimations: ML, maximum likelihood, mean square, and map. Then what is best estimate? Best estimate is something which reaches Cramer-Rao bound, where the error variance reaches Cramer-Rao bound. What kind of estimates lead to that? When does our mean square be? Because all adaptive filtering are basically mean square. Least square also mean square. When does give rise to your best estimate? In fact, when everything is Gaussian, then this will be the best estimate. And some treatment requires to be given one lecture. So, that I will give, and another lecture I might give on some other forms of LMS. That I will let you know. If you are in touch with me, how do I don't know how to reach you out. Anyway, thank you very much for this.